So I want to claim that, just to give you some intuition, let's first think about a velocity field. The curl, I claim curl measures the rotation component. Of a motion. So if you want a fancy word, that measures the vorticity of a motion. It tells you how much twisting is taking place at a given point. Okay, so for example, if I take a constant vector field, where my fluid is just all moving in the same place, in the same direction, where this is just constants, then of course the curl is 0, because if you take the partials, you get 0. And indeed, that's not what you would call, swirling. I mean, there's no vortex in here. On the other hand, well, okay, now let's do another one where there's still nothing going on. Let's say that I take, the radial vector field, where everything just flows away from the origin. So that's f equals x comma y. Well, if I take the curl, so I have to take partial x of the second component, which is y, minus partial y of the first component, which is x, I will get 0. And indeed, if you think about what's going on here, there's no rotation involved. On the other hand, if you consider our favorite rotation vector field, negative y and x, then its curl is going to be, well, n sub x minus m sub y will be 1 plus 1 equals 2. And that corresponds to the fact that we are rotating. Actually, we're rotating at unit angular speed, so the curl actually measures twice the angular speed of the rotation part of a motion at any given point. So now if you have an actual motion, a more complicated field than these, then no matter where you are, you can think of the motion as a combination of translation effects, maybe dilation effects, maybe rotation effects, possibly other things like that. And what the curl will measure is how intense the rotation effect is at that particular point. Okay, so I'm not going to try to make a much more precise statement. Well, I mean, the precise statement is, what curl measures is really this quantity up there. But the intuition you should have is it measures how much rotation is taking place at any given point. And of course, in a complicated motion, you might have more rotation at some points than at some others, which is why the curl will depend on x and y. It's not just a constant because, how much you rotate depends on where you are. So, if you're looking at actual wind velocities in weather prediction, then the regions with high curl tend to be hurricanes or tornadoes or things like that. They're not very pleasant things. And the sign of the curl tells you whether you're going clockwise or counterclockwise. Okay, so curl measures, well, twice the angular velocity of the rotation component of the velocity field. Now, what about a force field? Because after all, where we got to this was coming from and trying to understand forces and the work they do. So I should tell you what it means for a force. Well, the curl of a force field measures the torque exerted on a test object that you put at any point. So remember, torque is the rotational analog of the force. We had this analogy about velocity versus angular velocity and mass versus moment of inertia. And then in that analogy, a force divided by the mass is what will cause acceleration, which is the derivative of velocity. Torque divided by moment of inertia is what will cause the angular acceleration, namely the derivative of angular velocity. Maybe actually I should write that down. Oops. Okay, so torque divided by moment of inertia is going to be d dt of angular velocity. I leave it up to your physics teachers to decide what letters to use for all these things. That's the analog of force divided by mass equals acceleration, which is d dt of velocity. And so now you see, if the curl of a velocity field measures the angular velocity of its rotation, then, by this analogy, the curl of a force field should measure the torque it exerts on a mass per unit moment of inertia. So concretely, if you imagine that you're putting something in there, if you're in a velocity field, the curl will tell you how fast your guy is spinning at a given time. If you put something that floats, for example, on your fluid, something very light, then it's going to start spinning. And the curl of a velocity field tells you how fast it is spinning at any given time, up to a factor of 2. And the curl of a force field tells you how quickly the angular velocity is going to increase or decrease. Okay, so next time we are going to see Green's theorem, which is actually going to tell us a lot more about curl and failure of conservativeness.